Profit maximization in mechanism design. Abstract. We give an introduction to the design of mechanisms for profit maximization with a focus on single parameter settings. Introduction. In previous chapters, we have studied the design of truthful mechanisms that implement social choice functions such as social welfare maximization. Another fundamental objective and the focus of this chapter is the design of mechanisms in which the goal of the mechanism designer is profit maximization. In economics, this topic is referred to as optimal mechanism design. Our focus will be on the design of profit-maximizing auctions in settings in which an auctioneer is selling respectively buying a set of goods, services. Formally, there are n agents, each of whom desires some particular service. We assume that agents are single parameter, i.e. agent i's valuation for receiving service is VI and their valuation for no service is normalized to 0. A mechanism takes as input sealed bids from the agents where agent i's bid VI represents his valuation VI and it computes an outcome consisting of an allocation X equals to x1, x2, x3, and so on until xn, and the prices p equals to p1, p2, p3, and so on to pn. Setting xi equals to 1 represents agent I being allocated the service, whereas xi equals to 0 is for no service, and pi is the amount agent I is required to pay the auctioneer. We assume that agents have a quasi-linear utility expressed by ui equals to vi times xi minus pi. Thus, an agent's goal in choosing his bid is to maximize the difference between his valuation and his payment. To make this setting quite general, we assume that there is an inherent cost, C of x, in producing the outcome x, which must be paid by the mechanism. Our goal is to design the mechanism, i.e. the mapping from bid vectors to price allocation vectors, so that the auctioneer's profit, defined as profit equals to the summations of pi minus C of x, summing for all index I, is maximized, and the mechanism is truthful. Many interesting auction design problems are captured within this single-parameter framework. In what follows, we describe a number of these problems and show that for most of them, the VCG mechanism, Chapter 9, which maximizes social welfare, is a pool mechanism to use when the goal is profit maximization. Example 13.1. Single item auction. We can use the cost function C of x to capture the constraint that at most one item can be allocated by setting C of x equals to 0 if the summations of xi summing for all index I is less than equals to 1 and infinite otherwise. The profit of the Vicary auction, Chapter 9, is the second highest of the valuations in the vector V. If prior information about agents' valuations is available, then there are auctions with higher profit than the Vicary auction. Example 13.2. Digital goods auctions. In a digital goods auction, an auctioneer is selling multiple units of an item, such as a downloadable audio file or a pay-per-view television broadcast, to consumers each interested in exactly one unit. Since the marginal cost of duplicating a digital good is negligible and digital goods are freely disposable, we can assume that the auctioneer has an unlimited supply of units for sale. Thus, for digital goods auctions, C of x equals to 0 for all x. The profit of the VCG mechanism for digital goods auctions is 0. Indeed, since the items are available in unlimited supply, No bidder places any externality on any other bidder. Example 13.3. Single-minded combinatorial auction, non-bundles. In a combinatorial auction with single-minded agents, each agent has exactly one bundle of items that he is interested in obtaining. Agent I's value for his desired bundle, Si is Vi. We use the cost function C of x to capture the constraint that each item can be allocated to at most one bidder. Thus, C of x equals to 0 for all I and j. Si intersect Sj is not empty implies that xi times xj equals to 0 and C of x equals to infinity otherwise. Example 13.4. Multi-case auctions consider a network with users residing at the nodes in the network, each with a valuation for receiving a broadcast that originates at a particular node called the root. There are costs associated with transmitting data across each of the links in the network. The cost of transmitting across link E is C of E. Our problem is then to design an auction that chooses a multicast tree, the set of users to receive the broadcast, and the prices to charge them. In this setting, C of x is the total cost of connecting all of the agents with xi equals to 1 to the root, i.e. the minimal Steiner tree cost. In most non-degenerate instances of this problem, the VCG mechanism will run a deficit. One such example is the public project setting described in Chapter 9, Section 3.5, which can be mapped to a network with a single link of cost C, where one endpoint is the root and all the users are at the other endpoint. All of the other examples detailed in Chapter 9, Section 3.5, i.e. reverse auctions, bilateral trade, multi-unit auctions, and buying a path in a network, as well as many other problems, can be modeled in this single parameter agent framework.